In this lecture, I will give you a number of practical hints and tips which you will need to get your neural networks up and running. A nice and important result, which was shown by various authors independently in the late 1980s or early 1990s, is that a neural network really only needs one layer of hidden units to represent any function. Well, any Borel measurable function to be precise, meaning it has a finite number of discontinuities. So as it says here, an MLP, a multilayer perceptron or a neural network, with at least two layers of weights can approximate arbitrarily well any given mapping from one finite input space with a finite number of discontinuities to another, if we have enough hidden units. So that's very nice. It means that you do not need more than one hidden unit to represent any data set, as long as you have enough hidden units in that one layer. On the downside, however, finding the right weights in that neural network is an NP-complete problem. So there is a very good chance you really might not find the best set. But then, following this line of research with neural networks with only one layer of hidden units did not live up to their expectations. It led to the demise of neural networks in the mid-1990s. After all, the neural networks then showed they do not generalize as well as they really should have. So after approximately 1995, those neural networks lost in their popularity and research was no longer funded, and it was almost impossible to publish any paper with neural networks in the title or in the text. So what's the problem with multiple hidden layers? Well, first of all, of course, there is a computational cost. The more units you use in different layers, the number of parameters increases quadratically, of course, or at least multiplied with the number of units in each layer. And that computational cost can be problematic if your network gets large. And that was especially true, of course, in the 1990s. But there's another problem. In practice, it appears that the further away you get from the output unit, the smaller your gradient becomes, and this problem is called the vanishing gradient problem. Why is that? Well, remember, we have a residual at the output unit. That's usually already a small number, but that residual at the output unit, which is small, is multiplied with the weight into that and the activation of the neuron before that. So small number times a small number, and it gets smaller and smaller. So what happens, the deeper and deeper you get into your neural network, the smaller the gradient becomes. Look at the following example. Suppose we have the following data set representing the XOR function. 0, 0 is mapped on 1, and this is x1, that's x2, and that's z. 0, 1 is mapped on 1, and this should be 0, of course. 1, 0 is mapped to 1, and 1, 1 again is mapped to 0. Well, you can train this function to a neural network with two inputs, two hidden units, one output, with the corresponding weights, of course. That's your x1, that's your x2, that's your z. Well, if you do that, and you look at the weights, for instance, the weights going out of the first input to the hidden layer, your error function, your error surface looks something like shown in these pictures. And you see there are some more or less flat areas, but they are not too bad, and finding a minimum is really soluble. As we add more hidden layers, so in this case, for instance, we have 3 hidden layers, the flat areas become flatter. So there, in these areas, the gradient is very close to 0, and learning is problematic. In this example, with as many as 10 hidden layers, you see that we have many areas where the gradient is practically 0. You will need a very good learning algorithm to deal with that. But a paper by Hinton, Osendero and Tay in 2006 showed that despite the fact that one only needs one hidden layer to represent basically any function, adding more layers really improves the behavior of a neural network. They showed that deep neural networks, so networks with more than one layer of hidden units, generalize much better. The paper that was published in Neural Computation in 2006 demonstrates that on handwritten digit recognition, the MNIST database. To solve the vanishing gradient problem, an unsupervised layer-by-layer pre-training method, they called restricted Boltzmann machines, was introduced by Hinton and his group. Since then, deep learning has been successfully applied on many data representation problems and has outperformed many other methodologies in various fields of application. Since then, however, it was also shown that normal backpropagation can be used to train these deep networks even without pre-training. Important improvements were obtained by simply adding more data, training longer, and that's possible with GPUs, for instance, some improvement to weight initialization, and network regularization, for instance with dropout, which we will explain later. Why does adding more layers to a neural network work? Well, I know no rigid mathematical explanation, but this slide by Joshua Bengio gives some indication of what is going on. It assumes that the neurons present certain features of the data that is coded in the neural network. So neurons close to the input, they learn to represent low-level features. A good example is the convolutional neural network, which I will show later on. Lower layers learn to filter lines or represent lines in an image. And the higher layers can then build more complex features based on the lower level features. And you can repeat that and repeat that. And these complex features create more and more abstract representations of what is found in the data. What sometimes also improves learning is the use of different activation functions. The so-called rectifier linear function, max of 0, x, so that's this guy, often works well as the discontinuous version thus. Basically, that function approximates the summation of many sigmoid functions, and you can expect it to represent many hidden units in one. The use of this activation function reduces the vanishing gradients. There are also some cases, however, where it really doesn't improve your learning at all, and you just have to try to see if it works for your particular neural network and your particular dataset. I mentioned regularization before. How does this work? Dropout is a method which was introduced by Hinton et al. In 2012. It is a very simple and highly effective way of regularizing weights. It works like this. During training, each hidden unit is switched off with a certain probability, usually a half. That means that with this probability, the hidden unit outputs 0 rather than its computed value based on its input and the weights. This leads to a system where weights are shared between different hidden units, and it prevents single units to represent specific parts of the data. It leads to a very strong regularization. It is much better than the previously used L1 or L2 regularization, which pulls the weights to 0. Instead, what dropout does is that it pulls the weights to what the other neurons want it to be. To compute the output, we can just take the output of a hidden unit and divide it by 2, while that assumes, of course, that the dropout rate was half during training. Here's one important rule of thumb. If you're training and your neural network overfits your data, you need to use dropout. And if you didn't use dropout and it doesn't overfit, Most likely your neural network doesn't have enough hidden units and you need to make it larger. Remember that in the first neural network lecture I introduced this method of learning. For a specific sample, you compute the output of your neural network, you compute a residual, you propagate it back, and then you adapt your weights. While this method works, it is usually not the most efficient way of learning. After all, the gradient, which you compute here, is used for each sample of the learning set, and that leads to erratic behavior. Furthermore, it is costly due to the weight adaptation for each sample separately. Instead, one usually learns on batches of data. Typically, a mini batch of several thousand data points is used, over which the gradient is computed. So you select your sample from a mini batch, you do your forward pass, you calculate your gradients, but you sum your gradients. And after this mini batch, then you update your weights using those summed delta weights. Of course, it is important that the mini batches be balanced. For instance, if you're doing classification, you want that each class has the approximate same number of data points in each mini batch. A next issue is weight initialization. While there exist some very intricate and efficient methodologies, there are two basic principles. First of all, you really need random initialization to break symmetry between the weights. Otherwise, all neurons would learn the same thing and no successful learning would be possible. Secondly, you need to scale the weights related to the number of inputs to a certain neuron. When it has many inputs, the weights must be correspondingly reduced in size to prevent overshoot. So typically, you take proportional to the FFNN the number of weights coming into a neuron to scale the weights down. But at the same time, it is important to shift the inputs to be around zero. That very much regularizes the error surface. For instance, in this example, if the inputs have a large offset, the error surface can be strongly elongated as shown here. Subtracting the mean of those input data leads to a much nicer error surface and therefore a better gradient. For similar reasons, scaling the inputs is just as important. If one input has a range 100 times larger than the other, then the error surface is elongated by a corresponding factor. Scaling your inputs solves this. In general, input decorrelation can improve the error surface. If you do so, you're basically making the axes of your data perpendicular, leading to an error surface which is more circular and less elliptical. In some cases, using principal component analysis to prepare your data may lead to a good speed up in learning. However, results with this are somewhat mixed. Sometimes it works and sometimes it doesn't. The methods we just discussed are focused on improving the gradient. Let us now look at how we can use that gradient. In the optimization lecture, we have looked at the momentum method to get improved learning speeds. Indeed, that's one of the most important methods to get gradient descent to work well. But there are a few other tricks, of which I want to explain a few. Despite the above gradient regularization tricks, it is usually still the case that your error surface is not as nice and convexish as you would like it to be. To deal with that, you may want to have different learning rates for each weight. After all, your error surface typically is flat in one direction and steep in the other. Remember the Hessian, right? It usually has something like this shape, or even worse, where the search direction in one axis is much larger than the search direction in the other one. So rather than having a single global learning rate, we can introduce a learning rate for each weight separately and use some very simple rules to find those learning rates. The method works like this. If the derivative of the error function for a specific weight keeps its sign, so the product of two subsequent derivatives is greater than 0, it doesn't flip, then we can safely increase the learning rate for that particular weight. And if it flips, well, then we quickly decrease it. A learning method called rprop, which was introduced by Miller in the 1990s, goes one step further. It uses only the sign of the gradient rather than the gradient itself. It is of course a very good way of ignoring singular Hessian matrices and thus ignoring flatness of the error surface. To find the learning rate, it uses the above method to determine the learning rate per weight. If the gradient sign is stable, increase the learning rate. If the gradient sign flips, decrease the learning rate. Rprop fails if one uses mini-batches. Take the following example. Consider a weight that gets a gradient of 0.1 on 9 mini-batches and a gradient of minus 0.9 on the 10th. So the weight perhaps shouldn't change that much, but rprop would increase it 9 times and decrease it only once, so it would grow a lot. How can we solve this? Well, you can see rprop as a method which follows the gradient divided by the size of the gradient. In the extended version rmsprop, we don't divide the gradient by the size of the gradient, but rather by a moving average of the size of the gradient, computed for instance like this. So we take the square of the gradient over subsequent mini-batches and then divide the gradient by the square root of that mean square. To summarize learning methods. First, for full data sets which are not too large, you may want to refer to full gradient methods such as conjugate gradients. They're very stable. But in most cases you will use mini-batches and revert to the more stable learning methods mentioned here. A new class of stochastic learning methods has been developed in the last few years. To name a few, Adam, Ada delta, Ada grad, Nesterov momentum are usually very good methods for optimization in neural networks. Depending on the data, one or the other may work better. But it does remain a fact that neural network training is not black box. Since the neural network structures and the data you train on differ widely, you will have to manually tune many of your parameters in your training procedure before you get excellent results. Besides all of the above, there is one important thing you must almost always do, and that is early stopping. You want to split your data in a training set and a cross-validation set. While you do your training on your training set, you want to evaluate how well your neural network performs on the data that you have not trained on. As shown in this figure, your training error is usually much lower than your cross-validation error, especially as learning proceeds. You want to use those weights where the error of your cross-validation set was the lowest. But then, if you want to report your error, you need to do this over a separate testing dataset. After all, the weights you previously selected were optimal for your cross-validation set. So to be fair, you must train like this. First, you split your data in a learning set, a cross-validating set, and a testing set. As usually you don't have infinite many data, you take something like 60 or 70% of your data for training, then 15 to 20% for cross-validation, and the rest for testing. So you train your network on your learning set, you test your network on your cross-validation set, and you repeat that until your cross-validation loss doesn't decrease anymore for as long as you think it shouldn't. And then you select the weights with this lowest cross-validation error, but you report your error on your testing set. So as you have seen, a neural network has many hyperparameters. If you want to design your neural network, you have to answer questions as how many layers do I need? How many hidden units per layer? Should I better use a sigmoid or a rectifier activation function? And so on. Now it is certainly a good idea to get a bit of a feeling which knobs you have to turn to get better performance. But to get the last bit out, a hyperparameter search is the only thing you can really do. It means that you evaluate many versions of your neural network, each with its own set of hyperparameters, and see which ones are the best. Or if you want to do this, you may want to look at the Abscess hyperparameter optimization package you find at GitHub. It was developed by a student in our lab. A final thing. All of the above has been explained with regression in mind, but you can use neural networks just as well for classification. There are two important things you want to take into account if you do that. First, if you do classification, you may want to interpret the output of your neural network as the probability that your output is in a certain class, given the current input. So you want to predict P of C0 given X, or of course, the reverse for C1. But if you do that, the likelihood is actually a Bernoulli distribution. And computing the negative log likelihood leads to this different loss function. So whenever you do classification with a neural network, please use a Bernoulli rather than a Gaussian assumption. And of course that means you want to use one-hot encoding for your classes. So your classifying neural network has as many outputs as you have classes. For your data in class 1, the first output is trained to 1 and the others to 0. For your data in class 2, the second output is trained to 1 and the others to 0. And so on.